All right. Thanks, Lena, for organizing this and for the introduction. Hi, everyone. Thank you for making the time for yet another talk today. I guess this is a very charged day. This is my first seminar since the pandemic that is in person, so I'm very glad to be able to stand up in front of someone, finally, not just in front of my computer screen. It feels much nicer, I have to say. So what I'm going to talk about today is, generally speaking, interstellar medium in the center of the galaxy, and I'll focus mostly on two different scales, on the parsec scale and the sub-parsec scale. So to give you a quick overview of, let's see if this works. Yes, this is the outline of the talk. I'm just going to introduce very briefly the Galactic Center. Then on the sub-parsec scale, I'll talk about how we monitor the center of the galaxy, and that allows us to find compact cloudlets that are probably part of population of dust storm shrouded stars. I'll talk about a little bit about the accretion flow, and then I'll move at larger scale, where I'm going to talk about the gas that is orbiting around the black hole at around 1 parsec. Okay, so let's move on. The center of our galaxy. Well, when you say galactic center, different people mean different things. For me, center of the galaxy is really the central few parsecs and even the sub-parsec scale. So at this scale, we find a huge number of stars. In the central parsec, there are about 10 to the 6 stars in the central cubic parsec. And most of the stars are old red giants, but most of the radiation actually comes from young stars, OB and Volbright stars. So this is a Hubble space image of the center. The central parsec is around this area. The stars there are organized mainly into different populations, the young stars at least. Okay, so we have a young stellar cluster, and some of the stars are actually on a disk around the black hole. Here is the galactic plane. So, of course, stars can tell us a lot about the center of the galaxy. Thanks to the study of the motion of the stars, we were able to discover and prove that there is actually a black hole at the center of the galaxy. And this, of course, was recognized in 2020 with the Nobel Prize in Physics to Penrose, Guest, and Genzel. So we know that at the center of the galaxy, if we look at the stars here, these are images coming from the Keck telescope that show about 20 years of data of the stars orbiting the innermost region. And if you look, everything is moving in this video, but in particular, there is this star. This is called SO2 or S2, if you ask the German group, that is making a full orbit around the center, and that's the star that allowed us to prove that there is a supermassive black hole there. At 4 million times the mass of the sun black hole, adopt a Sage star. Sagittarius A star or Sage star for sure. Okay, so these are the stars. They're very interesting. They can tell you a lot, but the type of data that you gather to study the stars and get all these amazing results actually give you access as well to the interstellar medium. I'm just going to do this faster. So this is the same scale as the image we were looking at before, but this is now the interstellar medium we're looking at. So there are mainly two structures that we see here at this scale, the circumnuclear disk and the mini spiral. So the circumnuclear disk is a torus of molecular gas that is made of several different clumps that is rotating in a quasi-circular motion around the supermassive black hole at the center. It's very clumpy and regular, but it can be roughly modeled as a torus in circular motion around the center. We know that some gas that has been traced through ionized gas is falling toward the center, but as it is right now, this is the larger reservoir of matter close to the supermassive black hole, but is right now kept a distance from the black hole itself, most likely from the wind coming from the stars of the central cluster. So this at some point is material that is going to accrete onto the black hole, but we're not quite sure exactly when and how. But yeah, this is a kind of structure that you also see in other galaxies that often have tori of gas around their center. So the inner cavity of this disk is ionized by the UV radiation coming from the young stars in the center as well. So it's kind of an interesting environment. So as I was saying, some ionized gas has been traced to be looking like it's falling toward the center along the arms of what we call the mini spiral. This appears like ionized gas, but it's most likely just the ionized surface of probably larger clouds. So this can be either material that has been stripped from the C and D circumnuclear disk and is falling toward the black hole, or it's maybe a part of other clouds that were orbiting outside and got trapped by the black hole gravity. So in addition to these two structures, one thing I'm going to talk about is that there is a lot of, well, not a lot, there is some molecular hydrogen also inside the inner rim of the circumnuclear disk in this very ionized environment, which is surprising. Okay, so this is kind of—
the surface density, is a mass distribution really truncated and there is a well-defined cavity, or if you account for all the mass, ionized, neutral, and so on, is it continuous?
It is not continuous.
It is not. So there is a real cavity.
There is a cavity, and this you can see that these parts are ionized and they have different type of excitation, and you have denser clouds all along this, whereas the density drops inside the cavity. Is
self-gravity important in circumnuclear disk?
Yes, even though it's not clear if it's actually self-gravitating or not, because estimating the mass is not super straightforward actually. And so I think there are different papers that say different things. There have been arguing about the total mass of the circumnuclear disk as well. But yes, one of the questions is it self-gravitating or not? But most people seem to believe that this is a transit structure that is going to eventually just drop onto the black hole at some point. And,
but what is the mass? What is assumed for the mass of this thing?
So there have been several order of magnitude difference actually. So
that's okay, whatever.
I now have to remind myself exactly which one is the most trustworthy one, but it's let me think. I can't remember right now. It's pretty consistent. These are big clouds.
You asked for circular. Which one? Which
the
CND? I think it's 10⁵.
10⁵.
Yeah, but some people say more, some people say less. Yes, I guess.
Like at least what I saw, maybe I'm not looking the right one. Like someone says 3 10⁵, someone says 3.5 10⁵, someone says 4.
No, but some people say also much less. I mean, I think the people that say much less are not maybe one of the most recent publications. So maybe 10⁵ is more accurate.
Just trying to compare with the mass that was claimed for these disks of stars, of sort of young stars that are supposed to be on a smaller scale, like 10 times smaller scale, right?
Yeah, this is the scale of the
and those are of the order of 10⁴. That's what was claimed in total. So I mean, there is sufficient amount of mass, looks like, in the circumnuclear disk to form these stars on the inside. I mean, but during the next episode.
Yes, so there is no evidence of ongoing star formation right now in the circumnuclear disk, even though we expected maybe to have, but I haven't seen any convincing evidence of star formation happening right now. So what we think, I mean, what was proposed by Mark Morris in a paper a few years ago is that there are cycles of activities that go on. So right now, the CND is kind of kept at a distance. Most of the material is not enfolding on the black hole, but at some point, if it's the wind, for example, that is pushing it away, the wind from the star, once the stars evolve and it sees the wind, then the material can actually accrete into the black hole and trigger a stronger star formation, a stronger activity in the black hole, but also initiate star formation because of increased densities and so on in some parts of the clouds. And then you form stars again that push away some of the material and you start the cycle again. So that's one idea that is kind of nice.
You also, like, there is more stuff before we go, right? So
yeah.
For example, the mini spiral is like few hundred of solar masses. And the next one is bigger, and the next one is going to be bigger. Like, if you just simulate the mini spiral, there's definitely not enough mass.
Yeah, the central molecular zone has a lot of bigger clouds, but they are further out, so you still have to figure out how to get those to these scales before you can accrete them onto the black hole. But this is a problem in every galaxy, right? How exactly to get the material from 100 parsec to the central parsec and then onto the black hole. It's not super easy to understand how this mechanism works, how you remove angular momentum and so on, which kind of phenomena does that.
So we're running some simulations, which we, there is a student who works on this, so we're simulating the circumnuclear disk as a ring, just not this one, and then see how it evolves. And pretty much in about 1 million years, the thing starts accreting like crazy. You will have stars.
Only 1 million years? That seems pretty short century.
I mean, yeah, but so far we just have
with a simple
Wolfram stars, which are close to the whole thing. But it's just like
what's driving the exchange of angular momentum in the disk that starts falling in.
So sorry, stars.
I mean, why the disk starts losing angular momentum?
I mean, there's not that dense, right? But you have much more accretion. You have like disks forming close to the black hole where you can potentially form more stars, I assume. But we're pretty much stopping it as soon as it's starting accrete like crazy.
So the 1 million year is it given by the orbits of the Wolf-Rayet stars and the evolution of the Wolf-Rayet stars, or what is it? Is it that it's driving?
I mean, because if you set up the structure, you have a ring rotating, what is supporting your ring, right? Nothing is supporting.
Well, centrifugal force, presumably. I think
Yeah, but it's also made of gas, right? So it's not made of planets or something.
Okay, we should probably let.
No, this is interesting. I think it's
markers on the paper.
yeah. So it's also complicated because this is not a perfect ring either. It's very, very clumpy. How clumpy it is not super clear either. So there are a lot of parameters that we don't know about the CMD that I think will help us understand better or measure better what is its future. It's complicated. Okay, so so let's go back to the very central zone right now. So I was telling you I'm interested at two scales. So the scale where basically the CND transitions into the cavity, the ionized cavity, and the very central region. So as we see, the CND is maybe gonna accrete at some point, most likely it's gonna accrete, but right now it is not. So maybe there is some smaller scale phenomena we can see to trace accretion onto the black hole, completely different scale, just very tiny ones. But you know, this is our easier chance to look at accretion onto supermassive black hole because it's the closest one to us. So if you focus on the very central region, 0.01 parsecs, so much different scale now, these are the orbits of the stars that are part of the what's called the S stars cluster. Those stars that orbit very close to the supermassive black hole. These stars, there is one that is particularly famous. It's SO2 is the one that allowed two groups at UCLA and at the MP in Munich to measure the gravitational redshift for the first time in the environment of a supermassive black hole. So stars are great. They told us that we actually have a supermassive black hole at the center of the galaxy. They allow us to test general relativity in the regime of a supermassive black hole. But there are also other stars, other things that orbit the black hole that are interesting. For example, G1 and G2. These are objects that have been discovered kind of recently in the last decade. Especially G2 is the most famous one. They are objects that appear to be made. I mean, their emission appears as dust and gas emission. They are kind of large, probably a few hundred AUs, and they come very close to the supermassive black hole. In particular, G2 was discovered only a few years before its predicted closest encounter with the supermassive black hole. And since the emission was just dust and gas, as what people saw, they thought it was a cloud or a clump, and that it was going to accrete onto the supermassive black hole. So people got very excited because that would be a lucky chance to actually see accretion happen near a supermassive black hole in real time. So this is kind of the expectation of what people thought was going to happen to G2. Here in red is G2, and they expect when it was getting closer to the black hole to be completely disrupted by its close encounter with the black hole.
So they are resolved, right? I mean, you do measure their sizes.
Sorry?
You do measure their sizes.
Yeah, well, you have an issue with resolution. Sometimes they're unresolved. So they are, I think only slightly resolved or completely unresolved. So you don't have a precise estimate of the size all the time. But yes, this is kind of an upper limit. But this is a simulation of what people expected to happen, which didn't really happen because G2 during its closest approach got elongated, but it didn't get completely destroyed. It survived and it became compact again once it passed the periapse.
And the pericenter distance was what?
I think I had it here in the previous slide. Well, I think it was a few hundred AU.
And the object itself was few hundred AU as well?
Yeah, so the idea is that since it's the same range, they probably can accrete material onto the black hole.
It's just weird because, well, I mean, the Roche radius for solar mass object would be just 1 AU. So this thing is 100 times bigger.
Yes, they are very puffy. Yes.
And why did it not get entirely destroyed?
So what we think is that, I mean, it depends what group you ask. I'm going to get into more detail about this, but what we think is that probably part of its outer shells were disrupted and they got accreted onto the supermassive black hole. They might be tied to an event of increased activity that we did see a few years afterwards. But what happens is maybe most of the star and the dust were still down to the star, and then basically gas that we saw at the beginning was reformed. That's a possibility. So you unbound part of the gas, not all, then you replenished it from the dust.
But the object before the encounter seemed to be more or less like steady.
What do you mean by steady?
Well, it wasn't changing its size, it wasn't expanding. I mean, why would it
Well, also
form something after?
we have not been observing them forever. So for example, G1, we only observe it after it went to its closest approach. So we don't know exactly what happened before it. So we know that G2, I mean, it's a bit complicated because in the data where the object is going close to the black hole is not of great quality. Keck and VLT, they both were trying to observe it. Keck had some signal to noise issue for which we never were able to actually detect the object near closest approach and actually get some clean data out of it. And when you look at the data that comes from the VLT, they claim an elongation of the object, but the data is kind of noisy as well because it's the closer you get to the black hole, the crowder it is. So it's harder to actually get clean images out of it. So there are a lot of uncertainties of exactly the size and the measurements and so on. So, but what we are sure about is that we saw it before and we saw it afterwards. Yeah, that's what we believe for sure. And everything else is a bit drowned into the measurements noise.
So you said it was only marginally resolved. Is that size estimate of a few hundred AU coming from the resolution, or is it coming from other arguments?
I think it's mostly coming from the resolution. Yeah. So this is what the literature told us up to 2014 about these two objects, namely.
Just looks like they should be totally tidally destroyed, even long before approach.
Well, it depends exactly how far they are and how big is the star. I mean, probably it's not a big star because we don't see any emission connected to it, but if there is dust, it could hide a higher mass star as well, slightly higher. I mean, the order of magnitude is going to still be kind of the same, a few solar masses.
But in any case, black hole is so massive that the Roche radius should be about 1% of the distance to the black hole. And it looks like from this estimate that, you know, the size of the object is somehow comparable to the distance. So it must be all outside of the Roche radius.
Yeah, so
that's a bit.
Yeah, so it depends on, well, I think we are pretty sure that the size is few hundred AUs. About the distance, it depends a little bit how you calculate the orbit that has uncertainties on them. So it might be that is slightly larger the distance they passed at. So I don't know because I haven't worked with this data specifically, so I don't remember exactly what are the uncertainties on this. I only know the order of magnitude about this, but
I wrote a small paper on this. I think if you look at the Germans would claim 400 AU, the closest approach. So, and I think Günther's paper claimed about 100-ish.
Yeah,
So like 200-ish AU approach, and then they claim the size, which is about the same size, but it comes from resolution.
Yeah, it's an upper limit on the size.
There is lots of hand wavy thing because, you know, if it was approaching 100 AU with a size of 200 AU,
Yeah, it would be just.
Yeah, but it did survive, so it must have been compatible with this somehow. So let's see. So the first hypothesis that was proposed for the origin of G2 was that it was just made of dust and clouds, and so they suggested that this kind of clumps could form from the collision of wind coming from stars in the region, and they expected it to be destroyed, which was not the case. It was also suggested that G1 and G2 are actually not on a filament. They have orbits that are similar, so not identical, and there are a lot of uncertainties again. So these are kind of the two hypotheses that have been presented at the beginning. This is probably made of clouds, of dust and gas, and it's maybe part of a filament. Another hypothesis that was suggested is this is a young Kitori type star, and basically the emission we see, we have a star, a small mass star hidden inside, and then we have a disk that got disrupted and produces the messy gas and dust emission that we do see, that creates this puffiness around the object. And this type of star could be coming from the stellar disk, for example. And the interesting thing is that this type of objects are common, T-Tauri stars, so we would expect to see similar objects also elsewhere in this region. Also, you have to be careful on how you extract the star from the disk, given the orbits and the kick you expect and so on.
So there was an old argument that actually for the lack of low mass stars in the galactic center region by Nayakshin and Sunyaev, who noted that, given the use of these sort of disks and so on, if there was a large number of low mass stars, several solar masses, let's say, like if you take saltpeter, given the number of bright stars, if you extend it, there should be a huge number of low mass stars. Those, given the youth, they would be producing a lot of X-ray emission, which is not actually seen. So this is an old argument, as I said, it was 15 years ago or so. People seem to have forgotten it, but it actually is a nice constraint on the number of low mass stars and T-tower stars that might be present in the region. So it might be useful to kind of revisit it, maybe.
Yes. So one thing we looked at, because what I'm getting at is that we find more objects like G1 and G2 in that small region. Instead of having 2 objects of the type, we see other 4. So it's 6 objects of that kind that look like puffy stars, let's say. So the question is, how do you produce these and where do they come from? And one idea is that maybe these are part of the S-stars population. And they are only the low mass part that is not detectable because it's under the detection limit. However, the stars are slightly older than the stars in the disk. So I don't know about the X-ray radiation, if that would be
because anyone checked whether they could be X-ray sources. It's 1 arcsecond. Under resolution is not so good, but still.
I don't think we saw any clear correlation with the point sources from Chandra. Right, because people have been trying to look at this infrared X-set sources in general in the central parsec, and there is not a lot of overlap necessarily. Okay, so the third hypothesis about the formation, we are not talking about where the star is coming from, if there is a star inside. We're just talking how do you get the puffiness around the star, basically. How do you get all this gas and dust formed? So one possibility is a disrupted disk, predatory star. Another possibility is that these are the products of a binary merger. This is interesting because we know that when stellar population gets formed, many of the stars form in binary systems, and we know that these binary systems merge. Especially near supermassive black hole, because of the eccentric causality effect, you actually enhance the merger rate. So you expect to see more mergers near supermassive black hole. And this is a messy procedure that allows one star to shed material from the other, and you expect to produce something that looks like the puffy stars we were just discussing before. Okay. So basically there are 2 main hypotheses. This is a pure gas cloud, G1 and G2 we're only talking about right now, or there is a small stellar object hidden inside. Just to summarize the things we talked about. So now what can we add to this debate? The Galactic Center group at UCLA has been monitoring the center of the galaxy for over 25 years, using both imaging and imaging spectroscopy, mostly in the K-band. So what I'm going to focus on is the imaging spectroscopy data taken by OSIRIS, the IFU unit at Keck. So what is interesting is that these are data cubes. So mostly these data are used to extract radial velocities for stars and then get the kinematics to calculate stellar orbits. But since it's a spectrum that you get, you can also look at emission lines from the gas. And we have, well, now 15, but at the time of this work, 13 years of data of the central few arcseconds taken very consistently with this instrument. So you can track, of course, the stars, but you can also see how the interstellar medium evolve. The problem about this type of data, which is great because it's very rich, is that it's complex and there are a lot of emission. It's a very crowded region, the center of the galaxy. So sometimes it's hard to disentangle different components. So I use this nice visualization tool that allows you to render your cube in 3 dimensions at the same time. So what I'm looking at right now, what I'm interested in is interstellar medium. So I'm removing the continuum from the stars. And I'm just looking at the Bragg gamma emission line connected to its ionized gas. So with this little tool, you can actually turn your cube around. And this helps you because sometimes, since you have so much emission coming from this region, you have objects that are superimposed on the line of sight. but they have often different radial velocities. So with this tool, it's easy to disentangle them and actually look for stuff, especially small compact things. And one interesting thing we noticed that there are several compact gas sources that consistently appear year to year. And this is another 3D rendering of the cube. The two special dimensions are this way, and this is the wavelength dimension. This huge emission here in the center, it's emission from bragg gamma that is most likely not associated with the center of the galaxy. It's superimposed in the foreground or background. All these emissions are more likely associated with regions closer to the black hole. And what we see are these several compact clouds that we keep on seeing every year after year.
And what are these?
These ones, these are residuals from the continuous subtractions for the stars. So they are nothing real. This is just a residual from the continuous subtraction. This describes like this.
Okay, and how do you know that these clouds are not?
Well, because we can trace them. If you only have one cube, it's very hard to do it. But if you have 13 years of data, you can track the same object and you can see if it's real. So
so this continuous subtraction of stars would be also time independent. So you can subtract one cube from another, and would you remove these elongated streaks? Or
yes, so you can do a slightly better job, but this is not affecting my measurement much, so I didn't bother worrying about it too much. This is a star that is in the field of view. It's not superimposed with the features I'm very interested in, so I was not worrying about it too much. But there are stars all over the place. So most of the continuum is well reduced. This is a very bright star that actually, I think this is probably a very bright star that also has gas emission around. So it's a bit harder to tackle it, to remove it.
It's just, these gas clouds, you are saying that they're gas clouds because they actually move in proper motion at a velocity space. But if you have such a streak and the star itself is moving, from which there is an incomplete subtraction.
Yes,
that might give you some contamination as well.
Well, but they are very different. You can disentangle them very well. This is a bragg gamma emission. This is basically noise, residual. The emission looks very different. If you extract the spectrum at the location of these blobs,
so it doesn't have to be emission; it could be absorption as well.
Yes. But the emission lines from these ones are very clear and very well disentangled from this residual. It's just this rendering that it's. I think giving you the idea that it's confusing, but for example, this star doesn't necessarily have an absorption line in bragg gamma, maybe as a different line, or as a bragg gamma absorption, but a different velocity than these objects. So it doesn't affect that very much. This is just residual emission all over the spectrum. So it looks very different from the emission lines from these objects.
What's the second black line? Second horizontal black line.
Same. Yes. And also remember, you can turn your cube around so you can see you can easily disentangle the streak that is the residual subtraction from just one compact emission that is localized. They look very different. They might cross each other if you're unlucky, but that will actually, since you have data from multiple years, that will allow you to disentangle them. So maybe let me show you this rendering that maybe helps. So here again is my cube. I have emissions that are both blue shifted and red shifted, so that's why I'm doing two different animations. So I'm cutting my cube around my my blob in the blue shifted regime and in the red shifted regime. So as you can, so this is the position of the black hole. These circles indicate the position of each blob or G candidate in 2006. This is the year we started observing with OSIRIS. And then you see the cubes evolve with time. This is 13 years of data. So as you can see, for example, this one that we call the G6 is moving this way. I think this got moved a little bit. Well, G3, it's moving up. And then G4 is moving this way.
What's the spatial scale on
Here?
This figure?
So this is probably about 1 second. Or less. Yeah, sorry, I forgot to put the scale on. I will show other images where it's more clear. So maybe this address your concerns. If you extract the spectrum, for example, of this one that is called G3, year by year, you have some emission that is superimposed on the line of sight that corresponds to that vertical bragg gamma line that is at rest velocity. For bragg gamma is not moving much. And the emission from G3 is actually changing dramatically its radial velocity, and it's a clean line detection that you can easily disentangle from the continuum. So basically we saw these objects move and change their radial velocity. So what we can do now is to calculate their orbits. So we have the orbits of all these objects, G1 and G2 as they were measured by previous computations, and these new objects. So in this rendering, the solid line is the part of the orbit that is between the observer and the black hole, the plane of the sky that contains the black hole, and what is in dot is behind. So just to show you the different orientation of the orbits, they are oriented in a lot of different ways. The eccentricities have different values and so on. And here there is the scale. So what is interesting is that this random orientation of the orbital planes resembles the random orientation of the orbital planes that we see for the S-star cluster that also behave in that way. So that's what I was getting at before, that maybe these two populations are connected and these are the low mass part of that population. But I'll get to that in a second with more details. Okay, so basically we find that all these objects have several common properties. They are all compact. They all have Bragg gamma emission. We cannot detect any K continuum emission, and they have higher proper motion and radial velocity change. So the question is, are these plus G1 and G2 part of the same population that have a common origin? What is interesting about this scenario is that when you only had G1 and G2, you could propose a lot of different scenarios that doesn't necessarily need to be common because it's just two objects. If you need to explain 6 objects now, you need a mechanism that can explain them because they are fairly common in this region.
But what is no K continuum emission? Does it mean that there is no infrared emission for them, or?
No, it means there is no stellar emission associated with it that we can see.
Okay.
So this is what all that it means. Basically, there is no stellar emission in K-band that we see associated with it, basically.
But we see not just bracket gamma, right? We see something else.
We see bracket gamma, very bright, and we see dust, thermal dust in L band, not for all the objects because sometimes is a bit tricky because it's a very crowded region and the resolution is not great at those wavelengths.
And temperature of this dust is what?
So the temperature of the dust is not super well constrained in the center of the galaxy, but it's 200 to 300 K, or even slightly more or less. Okay, so
Sorry, will JW still look at them?
well, we wanted to do a proposal to look at it with the nurse spec, but in the end we didn't finish it. So maybe in the next years we're going to look at it. There is going to be data on the Galactic Center from JWST that maybe we can use to see if we can see anything from this. But yes, looking at JWST, I believe there are some lines that would be interesting to look at because they can tell you, for example, that they have disks, these objects, and if they can be associated with emissions that we see for similar objects that actually have disks. So it's not because of spatial resolution that we will be interested by, because of different bands we would access for the first time with JWST that would be interested. Of course, here we are limited because it's the Galactic Center. We're basically only looking in the infrared, near infrared right now. But yes, we definitely want more bands. So this is an artistic rendering of what we believe these objects might look like or be like. Here is the black hole. Here, so we will have a star, 1 or 2 star masses, maybe slightly more, surrounded by dust that is here rendered in red. And then there is a shell of ionized gas, that is ionized by the surrounding radiation, rendered in bluish gray.
So the idea is that this gas is outflowing, or is it in hydrostatic equilibrium? What is the structure of this things?
So the idea is that if you think that these were formed, for example, from a binary merger, all this gas is shed during the merger process and is heated from the inside by the stellar source. Then you have gas forming on the outer around this dust, and this gas is ionized by the surrounding radiation. So dust heated by the inside, gas heated by from the outside. It will be the very simple.
Then build a self-consistent model of such an object, like at least 1D hydrostatic equilibrium.
Yes, no one has done it yet. So it's complicated if you, well, it depends also on the type of scenario you want to look at. For example, if you want to model how it would look like when you merge two stars, people have not done that yet to see. I mean, people have modeled star populations and how, when they would merge and how, but then no one has actually looked closely at what the produce of this would look like. So, I mean, if people want to start looking into that, it would be great. I think there are some people in Italy University of I think it's Pavia. I can't remember if it was Pavia or Bologna, but they wanted to look into that and just doing that kind of modeling. It has not been done yet.
There is this object, Sakurai object, I think it's called V something monoceros, I think. So that is believed to be kind of right now undergoing the merger, and it has this enormous outburst of.
That's different though, because very young mergers will be very unstable because well, not very unstable, but like they would show very high variability because of all the things that are going on. I think the mergers that we're observing right now, I think it's 1 or 2 or maybe 3 objects that we know there are actually mergers happening right now. They have variability that we don't see for these objects. These objects are pretty stable in their emission. So, but one thing is that this could be a much later stage of that kind of process, because if you imagine in Galactic Center, we believe that probably the latest star formation event happened 6 million years ago, and simulations have shown that when you form binaries, most of them will tend to merge early, so they will merge shortly after the star formation episode, and then so you would already have passed the phase where you're actually creating all this apparent variability where you can maybe still see the 2 objects or they are still interacting. This is kind of the phase after that, where you have a more settled center and you have just all this messy stuff around it that is result from that interaction, so the dust and the gas. That would be the idea.
I mean, in the merger, all of the action is taking place within a couple of solar radii, and the dust is at several hundred AU. How does it get out from the merger site to several hundred AU?
Well, because the merger happens little by little. So when you have the 2 binaries that orbit each other and then orbit the black hole introduces eccentricity oscillation in the inner binary, and so basically the 2 stars can start to get close to each other, but it takes several orbits for them to actually merge. How many? I think it depends on the distance from the black hole, the mass, and so on. So they start little by little to shred material one from the other. Maybe I can show you this image that is from a paper that went through that scenario. This one. So the stars stripping material from to the other before they actually get close enough to merge in one single solar object. So it's in this process that you would produce all that dust. Now, at what distance would that projected dust, how much dust and how long? That's not clear because people have not done the precise calculation or simulation about that, but that would be interesting to check, of course.
I think the idea is that the dust actually forms. I think you create an outflow, and as it cools, adiabatically, you start forming dust. Otherwise, of course, inside the star there is no dust. I mean, it's too hot.
Right.
So you need to expel this material, and it's like in supernova explosions, you also form dust. So this is how the dust would appear in this case as well. But it's not clear
to see why a merger would generate an outflow.
Well, you have these tidal tails throwing stuff out. I mean, some amount of mass would probably be lost.
Yes.
What is not clear to me is how you can create a steady state gaseous envelope, even if it's dusty or something, that can be so large and persist for a long time, because it will be cooling on a Kelvin-Countess time scale, which should be pretty short. So I mean, the difficulty, I guess, would be in building a meaningful physical model of such an envelope around the star.
Yeah, so I'm not
that would be long lasting.
yeah, no, absolutely. And I've asked people that actually look into this kind of things, and people have been telling me that it's possible to have this kind of objects in this kind of time scale, but I've not seen precise calculations from anyone. So these are all back on the envelope calculations, and people seems to be convinced that it's possible, but that's all I have as a detail. I think people should look into that more closely for sure. It's a fascinating hypothesis for us because it fits well with the story that they're telling us about the center of the galaxy. We have to have binaries, the binaries have to merge. We should see by now some of the products of these mergers. And these are the things that we find that might look like that. But of course, this does not prove completely. These are coming from that. They could be different kind of objects. I've been suggested some also fun hypotheses, like, for example, these are primordial black holes. There is primordial black holes that actually keep the object together, or they are small clumps of dark matter.
Sounds more realistic.
So these are all possibilities, but none of these have a precise measurement of how the dust and the gas should look like. So I'm an observer, so what I see is these puffy, dusty, gassy objects, and I know that they remain compact, but there seems to be a mass inside that keeps them together. There's another object that I see that it doesn't behave like that at all, so I'm going to show you in a little bit. So it seems to be a different thing. So I'm just trying to go through all the scenarios that could produce that kind of puffiness and that will fit well with what we know about this region already. Basically, that's the only tools that I have right now.
Is the orbital distribution similar to the S stars?
Yes, in the sense that it's all over the place.
So I guess the question is, if you go out to 1/10 of a parsec and spent the same amount of effort looking for these objects out of the 1/10 of a parsec, would you find them?
We would like to know that, yes. That's one of the things. So the merger hypothesis scenario is interesting because it's connected to the proximity to the black hole. For example, the T-Tauri star scenario is not. These are common objects that are all over the place. We should see that kind of objects anywhere. But if these are the product of binary mergers that are enhanced by the black hole, that we have to be able to find more closer to the black hole because we are supposed to see more of these objects.
You're saying they're associated with the black hole, but you haven't looked away from the black hole.
Yes, I know, but the problem is
you don't know that they're associated.
No, absolutely. So I'm saying this to say this is a way to disentangle whether these are merger products or not. But the problem is that it's hard to observe these objects. We have been looking at the Galactic Center for 25 years. We only discovered these objects recently. And that's because we have a lot of data. It's very easy to think they're a clump of gas or dust some other place. It's very hard to disentangle them from all the other emission that is around. So there is a difficulty in observing these objects and making sure they look like this, also a larger radius. So that is a limitation for sure. This is what we were just discussing right now, that they are on similar scales and they are similarly distributed like the S stars.
The distribution of their angular momenta appears to be consistent with isotropic.
Yes, I mean, we don't have a lot of objects, but yes, that's
okay.
Roughly the idea. So yeah, so this was just what I was talking about. These are all the possibilities that have been invoked. I think that now that we have 6 objects, we can scratch this hypothesis. I mean, we have a lot of these objects. This maybe could explain one rare event or something else, but especially G1 and G2 both, they survive the close encounter with the black hole. There must be something in it that it keeps it together. It's either a star or some other more exotic and fun things, but there must be something that keeps them together. So
quick question,
yeah,
they postration and then they assemble, but they lose any mass in the process. Is it hard to say?
It's hard to say. So when you look at G2 is the only one that we saw pre and post period. G1 only we saw it afterwards. So for G2 before and after looks pretty similar. It doesn't look like it's much dimmer than before. It seems the same size and so on. So if they lost something, they didn't lose a whole lot. Now exactly how much is hard to say, because when you look at the gas, you only see the emission from the outer shell of the gas. It doesn't tell you anything about actually how massive is the object or how much there is inside. So you have a limitation given your type of observations on exactly how well you calculate how much mass there is. So it's a bit hard to say.
And the infrared luminosity that they produce is probably not associated with the luminosity of the central source.
No, it is not at all. So the only luminosity we see is from the gas. So that's why they're interesting if you think about them in connection with the S stars. So given detection limitations, you don't see low mass stars. That could be part of the S star population. You only see the more massive and bright one. But if these stars that are usually under the detection limit actually merge and produce this gas that then is heated by the surrounding radiation, that would be a way to actually see them in the end. So I think we talked about this. This is why we like the merger scenario. And we just talked about this last point as well. Okay, so now something that is on a similar scale, but it looks very different. This is an object that has been discussed previously in literature. It's called X7. Oops, sorry. It's elongated object you see here. So this is the central few arc seconds of the Galactic Center. This is the tip of the northern arm of that mini spiral structure that I showed you at the beginning. This is just the tip closer to the black hole. Here you have the SO2 star, the one that makes the full orbit around the black hole. This is the scale of the orbit. And the G objects are, so G1 and G2 are here in this area, and these other objects are here around this area as well. So, for example, this one is one of the G objects. I think this one is G3. And this one is the object I'm going to talk about. This looks very different. It's very elongated. And it's not only elongated, but it's getting more and more elongated as time goes by. So here is, it's a bit small. I'm going to show you a better image, but it was kind of shorter and had a comet-shaped structure in the early 2000s, and now it looks much more linear and it's much longer. Oh, and this one is just to show you the estimate of the orbit of the tip of this object, just to show you the type of motion we can extract from just the tip of this, with a lot of uncertainty, because this is not even a compact object, it's an extended feature, so it's very hard to measure orbits. So this is showing you the evolution of this object in the OSIRIS imaging spectroscopy data and in the NERC2 imaging. So as I was telling you before, it's getting more and more stretched. And it was kind of, he had a flared appearance at the beginning and is getting more and more linear. And you can kind of see the same here, but here is lower spatial resolution. So one question you have when you look at this is, what is giving it this shape? Is it something that is blowing this gas and dust away, or is it something else? So we looked at these objects for the past about 20 years. And so basically here, this is the orbit of the tip, the position of the black hole. This is the inclination of the objects year by year. Here I'm not rendering the difference in length and shape, just the orientation of the objects. And what we observe is that there is a pretty constant orientation of this object throughout our observing period. And so the orientation of this object in the plane of the sky is not aligned with what we'd expect if it was, for example, blown from a circular wind coming out of the black hole, because in that case, you would see a variation of its inclination given the distance to the black hole. It is not aligned with stars wind in the region. There are a lot of both varieties in the region that have strong winds. It's a bit hard to exactly calculate what is the direction of the winds. This wind direction comes from a model from this paper, but there are huge uncertainties. So we can say it doesn't look like there is a clear correlation with the wind directions, but we have to take a check on the fact there are a lot of uncertainties in this measurement. So we cannot completely discard this hypothesis. And it's not aligned with the magnetic field either. But again, here, this is integrated on the line of sight. So what is happening actually locally might be different. So still possibility, but there is no straightforward, easy connection with any of this possible origin for the shape of this object. Another idea was that, is this connected with the jet coming out from the black hole? That suggested that there is a jet at a given angle coming out from the black hole, and the orbit of the tip of X7 doesn't seem to be crossing this jet in any way. So it doesn't seem like it's blown from this jet either. So what I did is a very simple calculation where I take a few points along this object, and I assume an angle with the plane of the sky and a velocity gradient along this object, and then I make each one evolve independently. So it's basically, it's a toy model of a test particle model. And this very simple model only takes into account the gravity of the black hole. And so this shows you that you expect to see an object that keeps its constant orientation in the plane of the sky and gets longer with time, just take into account the gravity of the black hole. So it looks like the tidal interaction of this object with the black hole is what can gives it its evolution in the shape very simply. This is really nothing fancy, but it reproduces nicely what we observe, both in the motion and the shape evolution of this object, and also in the radial velocities. We can extract radial velocity from the Osiris data along the objects every year. These are dashed lines, and this model produces lines, the solid lines. So we similarly see an inversion of the velocity basically between the tip and the tail. The tip and the tail, one of in particular, the head was more redshifted than the tail in the beginning, and then it switches. So it kind of reproduces nicely what happens. So only gravity alone can explain the evolution of this object. Now the question is, where does this come from? Is it part of the G object's population, or what kind of phenomenon produced it? So it has one major difference with the G objects, of course, is that this is elongated and is getting more and more stretched, whereas the G objects remain compact. And this one is farther out than some of the objects ever went. So it's not because it's a closed approach or anything. One likely scenario is that this has been formed by a collision. If you think again about the merger scenario, for the G objects, we were thinking about two stars merging, shedding dust around them, and then keeping this gas around the merger product and then creating gas around. Another possibility is that during this merger, depending on the angle or the eccentricities on the speed and so on, you can unbound some gas that will be unbound in a probably linear shape, and that could be the origin of X7 that is only connected to the original collision that formed at the beginning, but it's not correlated with anything in the field necessarily, because it only depends on the orbit of the original pair that created it. Another possibility is that a different type of collision, for example, a compact object with the red giants. There are a lot of red giants, and it's a very crowded environment. So you can imagine a small star, or even a brown dwarf, or a small mass black hole passing through the atmosphere of a star and ejecting some material. This is a nice model from Dale 2009. And I think this is a black hole passing through a red giant. And as you can see, you unbound a lot of material in this kind of linear way. So you could form X7 some mechanism that looks like this. And then after that, the gravity of a black hole took care of its evolution. Okay, so I think this is going to be the last thing I'm going to talk about, because then I think I'm going to run out of time. This is very quickly. So all these objects are interesting because they can trace phenomena happening in the center of the galaxy, binary mergers or young stars, or can give you access to the low mass part of the star's population and so on. But also they bring material very close to the black hole, so they can actually trace accretion. Our black hole in general is not very active. But in 2019, we detected an unprecedented augmentation in the activity of the black hole. So this is the emission coming from SO2, and this is the black hole. So usually the black hole emission looks like this, and that night at some point we got this huge flare. Never measured a flare like that before.
Like the whole image is getting dark and bright, and
I think
it's not really calibrated even for one source.
No, I think it's just during the night the conditions were not super uniform.
Oh, and so the image is like not calibrated on to make sure that one of the points is always bright.
So I think they might, I didn't produce this, but I think they are flux calibrated. It's just the quality of the data is not the same. Maybe there were cloud passing by, the laser was not working as well at some point. So I think it's the AO correction is not exactly the same all the time.
They're calibrated on something else, but in terms of Galactic Center, the cloud is passing by us, everything is separating.
Yeah, so you can calibrate the flux in order to rescale everything, but the depth of your image might not be the same just because of the conditions in the moment. So the question is, what produced this this activity, and this could be the delayed effect of the passage of G2, for example. So G2 went to closest approach 2014. This happened in 2019, so 5 years passed. Is it 5 years the right amount of time for a gas that had been stripped from G2 and then had made its way to Sagittarius star? Maybe. It's not very easy because we don't know a lot about the accretion flow, but I think that people have calculated that up to 6 years could still be reasonable for the gas to make its way to the black hole. So it's compatible. But so, but there's someone here that has been looking at accretion in the Galactic Center very closely. So Lena has shown this very nice alpha data that shows the detection of an emission in H30 alpha in the central region. And the interesting thing about this emission is that it's made of two peaks that seems to correspond to the two sides of a disk. So H30 alpha is a transition of the hydrogen that is from very high states. So if you have this kind of emission, you would expect to also observe Bragg gamma in the exact same spot. So we have all this Keck data. So when Lena showed us this result, we looked for this emission in the Keck data. What I did is basically combine the 13 years of data we have to create just one spectrum of this region inside this orange circle. And the answer is that we don't see any counterpart to this. The only emission that we see is this one that is not as wide as this line and doesn't show the same behavior. And this is the one that I've been talking about since the beginning, this superimposed emission that is not at the center of the galaxy, but elsewhere it's flat, nothing to be shown. So it's interesting because given the emission observed by Lena in H30 alpha, you would expect a Bragg gamma emission up here. But what we find, well, we only can give an upper limit, right? Is many order of magnitudes below. And we compared with only one model so far, but our limit is compatible with this model. This is the same paper where I got the direction of the stellar winds from. They modeled the interaction of winds from the Wolf-Rayet stars, and the interesting is that they produce a disk on similar scales as the one observed by Lena as well.
Don't they produce a bigger disk? They're supposed to be the voyage.
So I think they said they are not sure about the size of the disk. They're not sure how precise it's from their model.
So it's aligned with the grid. Yeah.
Huh?
Because their disk is aligned with the grid. With the American grid.
Yeah, so I when I asked them about the size, they said they were not sure about the size and they were not believing the size they got. So I just got it from them. So the question is, how would you?
I have a point because whatever the numbers in the paper was like 10 times more.
Then this one?
Yeah. Then whatever I claimed, their numbers are much bigger than mine. So that's
in the disk?
Yeah.
Well, because I asked them for the numbers in there, and that's what I got from them. I guess it depends a little bit on the geometry of the disk that you use and so on. But
yeah, there isn't much.
With huge uncertainties. So it's order, not even order of magnitudes, I think. But so the question is, how do you get this amplification? Maybe there is some peculiar excitation going on, so it would be interesting to look more into that. So I'm not gonna have time to look into this because I think it's late. So I'm gonna jump to the summary. So 20 years of data looking at the same region might sound boring, but it's actually fun because it allows you to access a lot of different things. We were able to discover a population of dust and rotted objects. We like the idea that they might be the products of binary mergers because that seems to fit well with other scenarios. But what is interesting, regardless of their origin, is that whether they can accrete material onto a supermassive black hole. And maybe the passage close to the black hole of one of these objects is connected with the unprecedented variability that we saw happening at the black hole. And thanks to the data, we can also put a very strong constraint or model of the accretion using the upper limit we get for Bragg gamma. And maybe this points out some peculiar excitation that is happening at the center. And so I'm just, well, in the future, we want to keep monitoring these objects, look for more, look in different bands, all those things we discussed already. And I'm just going to leave you with this image that is kind of nice of different fields of view and different results and things we can look at looking at the interstellar milieu in the center of the galaxy. We talked about most of them, not all, but just to give you an idea how fun this environment actually is. Thank you very much. Thank you.
Could you say briefly what the search for intermediate mass black holes
Yes.
is about? How
Yes.
that works?
So we've been looking for intermediate black holes for a while. There have been claims of intermediate black hole detections all over the place. One of them in the center of the galaxy is at the edge of what is called the mini cavity, a bubble of expanded gas around this scale over here. And basically there is a cluster and there is some gas emission. So there have been people that have claimed that there is a intermediate mass black hole there. However, we looked at this with the Chandra data and Keck data, and we were able to look at the proper motion of sources in there and the gas emission and in the infrared and in the X-rays. And according to our measurements, the emission that's coming from this area is actually more compatible with the collisions from wind, from the stars, more than the accretion disk of a supermassive black hole. Also, we don't see any variability, which we would expect for such an object, and it's pretty steady, so we don't actually see anything. So people have been looking at it, have been claimed there is one. We believe that probably it's more likely that there isn't one. Very sure. Yeah.
Any more questions? Thank you so much.
Thank you.
Thank you.